So welcome to yet another video in the subject of radiation biophysics from the 11th lecture. This lecture is brought to us by Professor Pater, which did a really good job at putting together a very decent presentation, which we're going to incorporate into this video as well. We are going to review the long discussed dose response curve, which is really important to know. This is a graph that sometimes the department asks students to draw, also called the survivability curve. We're going to discuss two theories that explain this curve, the target theory and the molecular theory. So let's get this show on the road. Now, the dose response curve is basically something that was observed. And I just want to get this right out of the way, this y-axis quantity. We have the total surviving objects out of the initial number of objects that we have. And we're always going to start this graph from 1. Why is that? Because if we had 1,000 organisms, 1,000 organisms in the beginning, 1,000 were still alive before we started applying radiation. And this curve basically measures how many died or how many rendered and activated. So in the beginning, we're also always going to have 100%. So when you're drawing this graph, always start from the point 1. And we're not going to really address this line. This is just a linear representation of this graph. So actually, I'm going to do us justice, and that is not justice. I'm going to do us justice and delete it so it wouldn't confuse us. This is what we really need to be looking at is the actual representation here. Okay, so what happens? As the dose increases, more fraction of our organisms perish, or more fraction, you can say, die. This is a super easy graph to understand. The more radiation I have, the less surviving organisms I have. But it is important because we are often asked to draw it. And again, if I had to draw it from scratch, what I do, and this is just real quick, you can skip it if you don't feel the need to go through it. I have the dose, and it's super important to label the axis. I have the n over n0, and I need to indicate n is my surviving individuals, n0 is the number of individuals in the beginning, you can say, or the number of all individuals. And I'm going to start with 1, and I'm going to slowly decrease, just like so. Very good. So we've drawn this graph, and there came two different theories to describe why are we observing this. Why are we observing this? We're going to discuss the first one, which is the target theory. The target theory says something fairly straightforward. It says, hey, look guys, what we have is that each molecule has the most sensitive part of it, and this is its target, the most sensitive part of it. And when the target is destroyed, then the molecule as a whole is destroyed. And that explains this graph. The target theory, basically what the target theory says is that the whole dose response curve, the whole you can say inactivation or damage of molecules is stochastic. And by saying stochastic, it's just a fancy way of saying this is statistic. This is random, or it's probabilistic. Basically saying that we can either get a hit or not get a hit in our molecule. And obviously it's based on some variables that we're going to go through in a second. And this says, okay, basically what sort of statistics are we talking about? Well, let's discuss number of hits. A number of hits really is the variable that we have here. How many hits is this molecule going to experience? And more importantly, how many hits is this target going to absorb? And you can call this target the radiosensitive volume. The radiosensitive volume. Radiosensitive volume. Because this is a volume in the molecule. And it can either be inactivated if it is hit once, or if it's hit twice, or maybe this is a really tough target, maybe it needs 10 hits. But it can't be inactivated by 1.5. There isn't such a thing as 1.5 hits or 9.228 hits. These values do not exist when we talk about number of hits. And these types of variables are called discrete variables. Discrete variables cannot assume any value within an integral. If an integral is 1, 2, 3, they can't assume any value. They can't assume 2.2. They're discrete variables. In this instance, they can assume integer numbers. And when we're talking about discrete variables, the statistic concept we are going to use is the Poisson distribution. And if you're at this level in the course where you're saying, oh, what the hell is going on here? I haven't really paid attention in my biostat class because I don't really have self-control up till the end of the year. It's a good point to take your time and understand and remember this, because you're going to have to memorize this anyways for, I believe it is week 14 for when we have the self-control test in biostats. So the Poisson distribution basically describes what happens statistically when we're dealing with a discrete variable. And this is our formula for the probability to get that amount of hits. So n, I have n here. N is my number of hits. P is obviously the probability of attaining that number of hits. V is the volume of the target. D is the dose that I'm applying. And E is just an exponential function used in the Poisson distribution. Now what we need to think about is that the bigger the target, the more volume I have, obviously the more the probability that I'm going to get those hits. Also for the more dose I'm applying, the probability goes up as well. And there's always a lot of it is always addressed. It is called the case of one hit, one inactivation. In case of one hit causes one inactivation, that means that if I hit this radiosensitive volume once, then the molecule is rendered inactivated. And in that case, I can easily calculate how many surviving organisms I have, because I can just calculate the probability of attaining 0 hits, because these are the only guys that are going to be surviving. Any guys that are going to get 1 hit, 2 hit, 3 hits, they're already gone, they're already dead. So really I'm interested in who survived. What is the probability that I have surviving fraction that I'm dealing with? And if n is 0, basically this is 0, and this whole exponent is going to be equal 1. So really the probability of attaining 0 hits in the case of 1 hit causes 1 inactivation, or my surviving fraction of molecules, my surviving fraction of organisms, you can say, and this is in the minimals, is equal to this exponent. What this really means is that if 1 hit causes inactivation, that means that my surviving number of surviving organisms, you can say, can be calculated by this thing. And this is just something that you need to understand. It's just an industry standard. And as far as industry standards are concerned, we have a concept called D37, and often we are using this number 37%, 36%. D37 just says the dose at which the fraction of surviving, you can call it organisms or individuals, fraction of surviving individuals drops to, this is not drops to 37%. And that's pretty much it. So if I have an X dose applied, and if I apply this X dose, I lose everybody but 37%. This dose would be my D37. This dose would be my D37. So that's all we really need to know about that. And what we really want to appreciate as well is being that it is probabilistic, and I'm just going to actually get this equation here because I find it good to look at when we're dealing with this graph. I'm going to move this over here. Let's see what we have. And this is very important to understand. Let's just say, and I mentioned that we can have a target that needs one hit and it's already inactivated. Or we can have a tougher target that needs 2 hits. Or we can have a very tough target that needs 10 hits. 1 is not enough, 2 is not enough, 9 is not enough. And if we plug this in to the survivability curve that we saw before, fraction of surviving individuals and the dose, we'll see this. And this is called the shoulder. And it's important to understand what it represents and why it's there, because it's often asked about. What is the shoulder? Where we mentioned that getting that number of hits is probabilistic. There is a certain probability that I would get 1 hit. But there is also a probability that I would get 2. And you can understand that if I'm asking what is more probable, getting 1 hit or 1,000 hits in that radio-sensitive volume, getting 1 hit is way more probable than getting 1,000. That means that if I'm dealing with a molecule that requires, or rather a radio-sensitive volume that requires more hits to inactivate, that means that for a longer time it's not going to be destroyed. Let's just say I'm dealing with this little pink representation of a bunch of molecules. Let's just say that at this point, or rather at this point, I have 1 hit, and at this point 2 hits, and at this point 3 hits, 4 hits. I still don't see a drop because none of them was inactive. They're just hitting, and once they're hit, they're not rendered inactive until I have 10 hits. So 8, 9, 10 hits, and now I can experience, and now some of my molecules are going to be rendered inactive. That means that the more hits I need for my molecule to be destroyed, or my individual or specimen or organism to die, the more hits I need, the longer my shoulder is going to be. So if I have the K hits is 100, that means that I can keep applying a very large dose, and maybe I'm getting 30 hits at this point, maybe 50, but it's still not going to inactivate my molecule because it's really, really tough. So the shoulder can be explained. I'm going to write this down here. The shoulder can be explained. Shoulder can be explained due to the need in multiple hits to render a molecule inactive. To render the molecule inactive. And this should make sense to us. That means that the more hits I need for that molecule to be destroyed, the more dose I would need to apply to start seeing that drop in my fraction of surviving organisms. And this is the shoulder, and it's due to the number of hits required, and it is probabilistic, of course. So the more hits I would need, the longer it would take me to get all of my fraction of surviving organisms dropping. Very good. And now there's another theory that said, okay, we realize that there's this graph, the dose response curve, but we don't think this can be explained, this whole thing can be explained with the target theory. We think it is a poor theory. And why is it a poor theory? And this molecular theory says such a thing. The dose response curve cannot be explained with the target theory, because not all molecules really represent the damage done in radiation. What the molecular theory says is that there's this one molecule that is associated with radiation damage, and that's the DNA. Any other molecule doesn't really matter, because any other molecule, let's say a protein is destroyed, the DNA can actually get processes in order or in motion that would generate more of that specific protein. But if my DNA is destroyed, there's nothing I can really do. And supporting the molecular theory is that it just so happens that in organisms and biosystems and different biological systems, it was observed that DNA damage is associated with radiation damage. That means that the more damage I observed in the DNA, the more damage I necessarily observed in the radiation. That means there's some sort of link here that needs to be addressed. And also, the more DNA damage I see, the more loss of biological functions I see, which is obviously very, very tightly close and tightly bound to radiation damage. And also, there's another interesting correlation. There's a relationship between the ability to repair the DNA repairability, to radiation sensitivity. And what do I mean by that? If a given organism is associated with a very low ability or a very low rate of DNA repair, it would be very radiosensitive. And if I'm very good at repairing my DNA and I do it really, really quickly and really efficiently, I'm not going to be very sensitive. And all of these factors contributed to the molecular theory saying, hey guys, it's not any molecule that has a radiosensitive volume, it's just this DNA molecule. When it's destroyed, we have the radiation damage. And now we're going to examine the different mechanisms that can cause that. And we have our two strands here. We know that the DNA is a anti-parallel double helix with two backbones. And basically, as you can imagine, if one backbone is broken, now I broke this backbone, DNA can actually, and it just so happens there are different proteins that would facilitate repairing this, and this is just going to slowly be repaired. This is just going to slowly be repaired. But what happens if both strands are broken? At this point, as you can imagine, it is an irreversible damage to the DNA, and the DNA cannot recover from this. So this, in effect, it's called a double strand break. I'm going to recover my DNA here. A double strand break is basically radiation damage. So double strand break is associated with explaining the dose survive curves when things start dying on me and plummeting down. So whenever I have a double strand break, I will have inactivation of the molecule according, or rather radiation damage according to the molecular theory. And this can happen in one of two ways. This can happen as a result of one ionizing event, or two independent ionizing events. And right out the bat, we should understand that it's less probable that two different events through space and time are going to cause the same damage here, because you need two different factors that are independent to cause this event. Even before we've discussed the mechanism of it, we just need to understand this is less probable to happen than this. It is more probable that we would observe the inactivation of this molecule by one event than two different events causing it. Very good. So what could really occur? What could take place? Let's just say I have ionizing radiation here. And this ionizing radiation came about and destroyed this part of the molecule, kept on going, maybe deflected a little bit, and destroyed the other backbone as well. And this is obviously a double strand break from the same radiation in the same event. But another mechanism can happen in which this radiation came about and destroyed one of these strands, kept on going, missed the other, but right next to the other it ionized an electron, or formed a radical, or had some sort of ionizing event. And this ionizing event kept on going, and then that event interacted with the other strand and rendered it inactive. In 2 points, this is caused by the same event of radiation, either directly ionizing both strands or directly ionizing one and indirectly ionizing the other. This is both caused by the same event. What we can also have, as you may imagine, let's just say I have one radiation dose here that breaks one strand and one radiation dose here that breaks the other strand. let's just say this is actually the same strand because it goes around, but let's just say it breaks this one. It breaks this one. And now we have a double strand break due to two different independent events. And again, a double strand break is something that the DNA cannot repair and cannot recover from. And this is what we really need to understand with regards to the molecular theory. The molecular theory says there is this molecule called DNA. DNA damage is the only thing that is associated, the DNA damage is the only thing that is associated with radiation damage. And the one event that cannot be overcome and repaired is the double strand break. This is what the molecular theory really says. Perfect. Hopefully you found this helpful. See you in the next video.